Alright, so everyone, so today we're going to talk about the t-distribution, and do so, I'm going to introduce this example here. So we have a coffee machine. It dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee inside the cup. Here's your cup, 10 ounces of coffee, but the amount varies slightly from cup to cup, which I think would make sense. It's not going to be exactly 10 ounces. Imagine all the drips and so on and so forth. Sometimes it's going to be a little bit less, sometimes a little bit more. And this is really what statistics is all about, is dealing with this variation. So here, what's happened is we've taken a random sample of 20 cups and we've created the sample. Here's all the measurements of each cup and the quantity that it has taken. And what we wanted to see is we want to create a 95% confidence interval and then determine, is there evidence that the machine is shortchanging customers? So in order to create a 95% confidence interval, the formula for a confidence interval, which you're not required to know, but what it is x bar plus or minus this z star value times the standard deviation over the square root of n. This is the standard deviation of the population. Nowhere here am I given this value. That's a problem. But what I can do is I can find the standard deviation of this sample. So if I go here to this calculator, and I've already taken the liberty to add these values into L1, if I do one variable statistics, and another thing I can do is I like to try and put, here's a check to see if I've entered the numbers incorrectly. The sum of all the values, I've put it incorrectly. But my standard deviation is, of this particular sample, sub x is 0.1935. That is of the population, or actually of this particular sample, sorry. S sub x is the unbiased estimate of the population of all coffee cups. This is the unbiased estimate. It's not the actual one, but it's our best guess. And so because this is a good estimate, we cannot use normal, but we can use what's called the t-distribution, the student t-distribution. And what the student t-distribution is something that looks like this. The red graph is the normal distribution, and the t-distribution for different n's have slightly different curves. So the light blue is n equal to 2. It looks like this particular graph. As n is 3, it's this one. And the tails are heavier, and the tail in the middle is lighter. As n gets larger, it approaches almost exactly the normal curve. And so the larger n is, the more approximately normal it is. And so when we do t-distributions, we think of it in terms of normal distributions, with the one caveat that the standard deviation is an estimate. We use the unbiased estimate of it. So we're using the t-distribution in this case. And if we're using the t-distribution, we are going to do a one sample t-interval. That's the name. And if I look here at my stats and my tests, I have what's called a t-interval. And when I do the t-interval, I can look at data or stats. It actually asks me for all, it's actually gone through and done it, and I am doing a 95% confidence interval. I can look at the data, which I actually have, frequency L1. I want a 95% confidence interval. I can calculate it, and I get these values here. It is my confidence, I get x bar is equal to 9.845. My standard deviation, my n minus 1, making sure it's the unbiased one, is 0.1986, n equals 20. Now, I put a line here because I'm not finished with my naming the test. I also have to consider what's called this thing called degrees of freedom. Okay? And the degrees of freedom in this case is actually 19. So degrees of freedom equals 19. And this is the parameter. is also shown as like this Greek letter or something like a V, 19. So officially able to test one sample t-interval, degrees of freedom 19. The reason why degrees of freedom are 19 is, imagine when we have all these values here for my sample. I have 20 values here, and it has a mean of 9.845. Well, if I have 20 of them, 19 of these values, these 19, can be any numbers I want. It doesn't actually matter. But this if these are random numbers, any value, then the 20th actually has a fixed value if I know the actual mean. And so that's kind of an elementary explanation of degrees of freedom, but I have freedom to choose 19 of these values, and the 20th one there's no freedom on. And so degrees of freedom for the t-distribution is always equal to n minus 1 is what degrees of freedom is equal to. And there's more conversations about degrees of freedom as we continue on with the course. It's n minus 1, so in this case it is 19. So we have our t-interval, we have our degrees of freedom. Now, in calculating this, we would have done x bar plus or minus this thing called t star, which you don't need to know, but we would have done the standard deviation, the unbiased standard deviation, over the square root of n, which in this case is 20. We are using the central limit theorem. However, n is less than 30. So this is actually a problem because n is not large enough. We are assuming the population is normal. It's not told to us, but we have to assume that in order to use the central limit theorem and do this calculation, because n is not large enough. So we want to interpret our confidence interval. If we interpret our confidence interval now, we know that we are 95% confident that the true mean in ounces of coffee is between these two values, which I can see up here. And now, the true value, we are hoping 10 ounces is in there. Is there evidence we're being shortchanged? Well, 10 is not in this confidence interval. So it's not reasonable to think that the mean is going to be in there. So as 10 ounces is not in the interval, people are being shortchanged. So in order to do a t-interval, we have to first thing name our test. We're going to name the test. And then we're going to show the numbers. We will actually show the confidence interval, and then we will conclude in context. Okay, it has to be in context. About this one's about coffee cups. So these are the 4 things you should consider doing when you name the test. Include the degrees of freedom, thinking about your assumptions and if you've used the central limit theorem.